All right, so it's time to deal with balancing redox equations, and not those easy ones that often come along with galvanic cells that you can do without any formal series of sequence of events, but we're going to look at some more challenging examples. And for our circumstances, we're going to limit our exposure to situations that occur in acidic environments. So let's take a look at one that is different than one you've seen in class. So here's an example where we see the permanganate ion reacting with peroxide to make manganese 2+ and then release some oxygen gas. This is the example when we did elephant toothpaste demo, where we took peroxide and added a catalyst, and the catalyst was a blackish kind of powder. It's very similar to what's going on here. The permanganate ion can act like a catalyst, causing the peroxide to break up, and in the process, it itself is reduced. First step in any of these problems: assign oxidation numbers. So pause the video right now, and on this screen, just on your iPad, write what the oxidation numbers are. All right, so hopefully you've assigned your oxidation numbers. Now let's take a look and see how you did. Remember that when you're dealing with a polyatomic, the total charges of all the oxidation states should add up to give you the charge of that polyatomic. So in this case, manganese must be +7. Oxygen is almost always -2, but we're going to see an example here in just a moment where it's not. Hydrogen would be +1. Notice in this case, hydrogen peroxide. That means we're dealing with the peroxide ion, which is O2 with a -2 oxidation state. That means that each oxygen assumes a -1 oxidation state. After all is said and done, manganese becomes manganese 2+, and oxygen gas is elemental, goes to an oxidation state of 0. Next step, break it up into half reactions. So I'm going to color code these just for clarity. So we know the manganese, the permanganate ion, MnO4, goes to Mn2+. And the other component, hydrogen peroxide, goes to oxygen. Don't worry, we don't see any hydrogen yet. That's not a big deal. Okay, we'll deal with all of this sequentially. So, first thing we're going to do is figure out how many electrons are involved in the transfer. And you notice that for the manganese, it goes from +7 all the way to +2, which means it has to take in 5 electrons. When it's being reduced, remember that means it's gaining electrons. So each manganese is gaining 5 electrons. Okay, so 5 electrons plus the permanganate ion gives us manganese 2+. Now, in the case of the oxygen, right, we've got 2 oxygens, and so it's going in total from a -1 to 0. Okay, but remember there's 2 of them, so really the overall charge, it's -2 to 0, so it's a gain of 2 electrons in total being oxidized. So 2 electrons getting kicked out there. Sorry, I misspoke there. I said taking in electrons. Absolutely not. This is oxidation. Okay, we're losing some electrons there. Okay, next step. This is where we're going to make sure that the species that are oxidized or reduced are balanced. And in this case, they're balanced. 2 oxygens, 2 oxygens. We're going to now use H+ to balance out our charges. And we're going to compare the charge on the left-hand side to the charge on the right-hand side, and you use H+ to balance it out. So over here we've got a total of -6. Over here we have +2. That means we're going to have to add 8 positive things to the more negative side. So 8H+ plus 5 electrons should give us the sum total of both sides equaling +2. Moving on to the peroxide half reaction, we see that on the left-hand side, it has an overall charge of 0. On the right-hand side, it has an overall charge of -2. So we're going to add 2 hydrogens in that case. Notice how that little step deals with our balancing hydrogen. And the final step for us is to use waters to balance out the oxygens. The only case where that really comes into play is with the permanganate reaction, and we're going to add 4 waters to balance that. Now at this point, we have to make sure that the number of electrons that are consumed is equal to the number of electrons that are produced. So we take a look at any disparity between the number of electrons in the oxidation and the reduction half reactions. You're going to notice pretty quickly we're going to have to multiply both equations, and I'll do this change in green. We're going to multiply the top equation by 2 and the bottom equation by 5. That ensures that we have 10 electrons consumed, 10 electrons produced. Once we're finished with this, we can then bring it all together and add it up. Why don't you take the time right now, pause the video, and add it up and see if your answer matches up with mine. Okay, so if you check your work, hopefully you've got something that looks like what I've got here in green. Now at this point we can cancel out things that appear on both sides of the equation. So electrons should always cancel in their entirety. But in this case there's some other things that cancel out. Notice we have 16 H pluses and 10 H pluses. Well, we can cancel out 10 of those. So all 10 of those go away, and the 16 is taken down to 6. Nothing else will cancel at this point, so then we can write our final answer, and we'll do our final answer in, well, let's just leave it as black. Why not? So we have 6 H plus 2 permanganate ions plus 5 peroxide molecules reacts to form 2 manganese 2 ions, 8 waters, and 5 molecules of oxygen gas. So, key thing, focus on the most common places where you're going to make a mistake. Assigning oxidation numbers. Take the time, check your work. Second place that I see students make a lot of mistakes. Pay attention to where you're putting electrons. Now if you see permanganate, it's a dead giveaway that the permanganate is going to undergo reduction. It's going to be reduced. Okay? But in whatever case, electrons are always going to be added, meaning treated as a reactant, in a situation where the charge becomes less positive. And electrons will always be produced when the oxidation numbers become more positive. So, take a stab at the homework that I assigned for Tuesday, and we'll have a little bit of a discussion briefly on Tuesday morning. Have a great weekend, you guys.